Try to imagine nothing. I mean it. Close your eyes for a moment and picture absolute emptiness, a perfect vacuum, the complete absence of everything. You cannot do it. And here is the strange part. It is not because your imagination is limited. It is because nothing, true, nothing, does not exist. It cannot exist. The laws of physics forbid it. Richard Feynman spent his career wrestling with this problem. And what he discovered was so counterintuitive, so profoundly weird, that it challenges everything you think you know about empty space. Feynman once tried to build physics without fields. He wanted to strip away what he saw as unnecessary mathematical baggage and describe nature using only particles. It was elegant, it was beautiful, and it almost worked. Almost. What happened when that theory failed is one of the most important stories in modern physics. Because when Feynman finally surrendered to the existence of fields, he did not just accept them grudgingly. He discovered that fields are not some abstract mathematical convenience. They are the most fundamental thing in the universe. More fundamental than matter. More fundamental than energy. And nothing, that empty void you just tried to imagine, turns out to be one of the busiest, most active, most mysterious things in existence. To understand why this matters, we need to talk about what you think empty space is. Right now, you are sitting in a room, or maybe you are outside. See all that air? Now imagine removing it. Pump out every molecule, every atom. Create a perfect vacuum. What is left? Your intuition says nothing. An empty box. A void where things could exist but do not. This is the picture that dominated physics for centuries. Space was thought to be a stage, an empty theater where the drama of the universe plays out. Matter and energy are the actors. Space is just there, passive. Waiting. This intuition feels so natural that questioning, it seems almost absurd. Of course, empty space is empty. The very definition of empty is the absence of stuff. But here is where physics gets interesting. Because when scientists actually investigated what happens in a so-called vacuum, they found something shocking. It is not empty. Not even close. The room you are in right now, even if you could remove every single atom, would still be absolutely seething with activity. What you call empty space is actually a medium, a substance, a thing with properties and energy and structure. Feynman was one of the physicists who figured this out, and the journey to that understanding started with a radical question. What if we could explain everything without fields at all? Let us start at the beginning. What is a field? Now, here is the simplest way to think about it. A field is something that has a value at every point in space. Think about temperature. Right now, at every location in the room around you, there is a temperature. Near the window, it might be cooler. Near a heating vent, warmer. You could, if you wanted, assign a number to every single point. The temperature at that exact spot. That collection of numbers spread throughout space is a temperature field. Now here is where it gets more interesting. Some fields do not just have a number at each point. They have a direction too. Imagine the air in your room. You think it is still, but it is not. There are tiny currents everywhere, little movements too subtle to feel. If you could freeze time and attach a tiny arrow to every molecule of air, showing which way it was moving and how fast, your room would look like a porcupine. Arrows pointing this way and that. That forest of arrows is a vector field. So far, so intuitive. Temperature fields. Wind fields. Nothing too strange. But then physicists discovered something remarkable. The forces we experience, electricity, magnetism, gravity, are not just forces. They are fields. Big. At every point in the space around you. Right now, there's an electric field value and a magnetic field value. Even if there is no charge there, even if there is no magnet, the field still exists. This was already a strange idea, but Feynman wanted to push further. He asked, Do we really need these fields? Or are they just a convenient mathematical fiction? Think about it this way. When two electrons repel each other, we say they do so because of the electric field between them. One electron creates a field, the other electron feels that field. But what if there is no field at all? What if electrons simply interact with each other directly, at a distance? Feynman, along with his colleague John Wheeler, actually developed a theory like this in the 1940s. It was called action at a distance. The idea was beautiful in its simplicity. Particles influence each other directly, without any invisible field mediating between them. No fields, just particles. It almost worked. The mathematics was elegant. The predictions seemed reasonable. For a moment it looked like physics could be stripped down to its bare essentials. Just particles dancing with each other across the void. But there was a problem. Several problems, actually. The first problem was light. Light is an electromagnetic wave, and waves by definition need something to wave in. If there is no electromagnetic field, what is light? You might say light is particles, photons. And that is true. But Feynman's own work on quantum electrodynamics, or QD, revealed something even stranger. Photons are not little balls of light flying through space. They are excitations of a field. Ripples in something that exists everywhere. Imagine a still pond. The water is there whether or not there are waves. Now drop a stone. The ripple that spreads out is not a new thing. It is the water moving. The wave is what the water does. Photons work the same way. The electromagnetic field fills all of space, always. A photon is just what happens when that field gets excited. When the field ripples. Without the field, there is nothing to ripple. Without the field, photons cannot exist. Here is where things get genuinely mind-bending. Feynman did not just discover that electromagnetic fields exist. He helped prove that there are quantum fields for everything. There is an electron field that fills all of space. There is a quark field. There is a photon field. Every type of particle has a corresponding field. And these fields exist everywhere, always, permeating every point in the universe. What are particles then? This is the revolutionary insight. Particles are not fundamental. They are not tiny billiard balls bouncing around in empty space. Particles are excitations of fields. They are what happens when a field, spread throughout all of space, gets energized at a particular point. Stop. Think about that for a moment. You are not made of particles. You are made of ripples in fields. Every atom in your body is a pattern of excitation in quantum fields that fill the entire universe. You are, quite literally, a disturbance in the fabric of reality. The fields are more fundamental than the particle. The fields are what is real. Particles are just what happens when fields get excited. But here's the question that haunted Feynman. What happens when the fields are not excited? What happens when there are no particles, no ripples, no excitations? You would think the field just sits there at zero. Perfectly still. Perfectly quiet. Seems. That would be nothing, right? Wrong. Brain. Nay. Quantum mechanics says no. Absolutely not. The field cannot sit at zero. It cannot be perfectly still. Why? Why? Because of the uncertainty principle. You have probably heard of the uncertainty principle in terms of particles. You cannot know both the position and momentum of a particle with perfect precision. But the uncertainty principle applies to fields too. You cannot know both the value of a field and its rate of change with perfect precision. If a field were exactly zero, you would know its value precisely. And if it were perfectly still, you would know its rate of change precisely. Both at once. That is forbidden. So the field has to fluctuate, even in its lowest possible energy state. Even with no particles present. The field jiggles and vibrates and oscillates around zero. These are called zero-point fluctuations. The vacuum energy. The energy of nothing. This is not optional. This is not something that might happen. This is required by the fundamental laws of physics. Empty space must have energy. What is shep? Nothing must be something. The vacuum must fluctuate. And here is the part that should keep you up at night. When you add up all these zero-point fluctuations from all the different quantum fields that fill space, you get an enormous amount of energy. Some calculations suggest the vacuum energy should be enormous, far more than all the stars and galaxies combined. This is one of the great unsolved mysteries in physics. Why does empty space have so much energy? And why doesn't the universe explode? We do not have complete answers. But what we do know is this: empty space is anything but empty. Let me give you a way to picture this. Imagine a box. A perfect box, completely sealed off from the outside world. Now imagine you remove everything from it. Every atom, every photon of light, every trace of matter and energy. You create the most perfect vacuum possible. What is inside the box? No. According to classical physics, the answer is nothing. The box is empty. End of story. But according to quantum physics, the box is absolutely seething with activity. The quantum fields inside, the electron field, the photon field, all the other fields, are fluctuating wildly. Virtual particles are constantly popping into existence and vanishing again. Pairs of particles and antiparticles appear for the briefest instant before annihilating each other. Now, you might think this sounds like philosophical hand-waving. Nice mathematics, but surely it has no connection to reality. But here's the thing. We can measure it. We have measured it. There's an experiment called the Casimir effect. Take two metal plates and put them very close together in a vacuum. According to classical physics, nothing should happen. There is nothing between the plates to push them. But something does happen. The plates are pushed together by an invisible force. Why? Because the vacuum fluctuations between the plates are different from the vacuum fluctuations outside. There is less room between the plates, so fewer types of fluctuations can fit. The pressure from outside is greater than the pressure from inside, and the plates get squeezed together. This is not theoretical. This has been measured in laboratories. The force matches the predictions of quantum field theory. Precisely. Empty space pushes things around. Nothing has measurable effects on something. Here is another way to see that fields must be real. Think about magnetism. You probably played with magnets as a child. You felt that invisible force pushing or pulling. What is that force? The traditional explanation is that one magnet creates a magnetic field, and the other magnet feels that field. The field carries the force from one magnet to the other. But Feynman showed something even stranger. Magnetic fields are not really separate from electric fields. They are the same thing, seen from different perspectives. Imagine a wire carrying an electric current. Around that wire, there is a magnetic field. This is why electromagnets work. But now ask, what is really happening? An electric current is just electrons moving through the wire. Now imagine you are moving alongside those electrons at the same speed. From your perspective, the electrons are not moving. There is no current. And if there is no current, there should be no magnetic field. But wait, there is still a force on nearby charges. How can that be? Here is the answer. When you move, the electric field looks different to you. Because of special relativity, the electric field transforms. What looked like pure electricity from one perspective looks like magnetism from another. The magnetic field is not something separate. It is what happens to the electric field when you start moving. Electricity and magnetism are two faces of the same underlying reality, the electromagnetic field. This unification was impossible to achieve without fields. Without fields, electricity and magnetism remain mysterious separate forces. With fields, they become one elegant, unified phenomenon. Feynman came to appreciate that fields are not just mathematical conveniences. They reveal deep truths about how nature works. Now let us go deeper still. Think about the forces between electrons. Two electrons repel each other. In Feynman's QD, this repulsion is mediated by the exchange of virtual photons. One electron emits a virtual photon, the other electron absorbs it. And the result is a force pushing them apart. But here is what is strange. These virtual photons are not coming from anywhere. They emerge from the vacuum itself. From nothing. Feynman developed a way to calculate all of this using what are now called Feynman diagrams. Every possible way that particles can interact, every possible path, every possible exchange of virtual particles gets added up. The sum of all these possibilities gives you the probability of different outcomes. And the calculations are astonishingly accurate. QED predicts certain properties of electrons to 10, 11, even 12 decimal places. The predictions match the experiments perfectly. This is like measuring the distance across a continent and being wrong by less than a human hair. That level of precision tells us something profound. The theory is not just approximately right. It is capturing something real about how the universe works. And what does that theory say? It says the vacuum is seething with electromagnetic field, constantly fluctuating, constantly creating and destroying virtual photon. Empty space is interacting with atoms and changing their properties in measurable ways. Nothing is mediating the force between everything. So what exactly is the quantum vacuum? Let us be precise. The quantum vacuum is not empty space. It is a medium. It is a playground of fields. Think of the universe not as an empty box where stuff happens, but more like a block of jello that is constantly being twisted, pulled, and warped. The jello is the fields. Everything that happens, every particle, every force, every interaction is a disturbance in that jello. You cannot remove the jello. You cannot get rid of the fields. You cannot stop the fluctuations. Even if you could remove all matter, all radiation, all energy, the fields would still be there. Still fluctuating. Still full of zero-point energy. The vacuum is not the absence of everything. It is the presence of fields in their lowest energy state. And that lowest energy state is not zero. This is perhaps the most important insight. The ground state of quantum fields, the state with no particles, no excitations, nothing we would ordinarily call stuff, still has energy, still has activity, still has structure. True nothingness, absolute emptiness, complete void. This does not exist in our universe. It cannot exist. The laws of physics prohibit it. So what happened to Feynman's attempt to build physics without fields? He abandoned it. But not reluctantly. He came to see that fields are not the burden he once thought they were. They are the key to understanding everything. Without fields, you cannot explain light. You cannot explain the Casimir effect. You cannot explain the magnetic moment of the electron. You cannot explain why atoms are stable. You cannot explain. You cannot explain anything, really. Fields are not a mathematical convenience. They are the most fundamental description of reality we have. And here is the beautiful part. Once Feynman accepted fields, he was able to develop the most accurate theory in the history of physics. Quantum electrodynamics describes the interaction of light and matter with precision that borders on the miraculous. The theory that almost worked, physics without fields, was replaced by something far more powerful. Something that does not just describe nature, but reveals its hidden architecture. Now, you might be thinking, this is interesting, but what does it mean for me? Here is what it means. You are not separate from empty space. You are patterns of excitation in the same fields that fill the vacuum. The electron field that gives your atoms structure is the same field that fluctuates in the emptiest regions of the cosmos. The photon field that carries light to your eyes is the same field that seethes with virtual particles between stars. You are intimately connected to nothing because nothing is what you are made of. Every atom in your body is surrounded by vacuum. Every particle is embedded in quantum fields. Every force you experience is mediated by virtual particles emerging from emptiness. When you look at the space between objects, you are not looking at absence. You are looking at the ground state of all fields. You are looking at zero-point energy. You are looking at the substrate from which all matter emerges. Wow, maybe science. I'm trying to know in But there is one more twist, and it is perhaps the strangest of all. The vacuum we live in, the ground state of all the quantum fields, might not be the true ground state. This is a prediction from quantum theory. Our vacuum might be what physicists call a false vacuum, a metastable state, like a ball resting in a small depression on a hillside, rather than at the very bottom of the valley. If our vacuum is false, it could decay. A bubble of true vacuum could form somewhere in the universe and expand at the speed of light. Everything that bubble touches would be converted to the new vacuum state. We would never see it coming, and we could not survive it. The laws of physics inside the bubble would be different. Atoms might not exist. Chemistry might not work. Life would be impossible. Now, before you panic, there is no evidence that this is about to happen. The universe has been around for 14 billion years without such a decay occurring. If the vacuum were highly unstable, it would have decayed long ago. But the mere possibility tells us something profound. Even what we call nothing, even the ground state of reality, is a physical thing with properties and dynamics. Nothing is not nothing. Nothing is something specific, and that something could, in principle, change. Let us step back and see the big picture. For most of human history, we thought empty space was simple. It was nothing. The absence of stuff. The canvas on which the painting of the universe was drawn. Feynman and his generation of physicists shattered that picture. They showed us that empty space is the most complex thing imaginable. It is full of fluctuating fields, virtual particles, zero-point energy. It has structure and dynamics and energy. This changes everything. It means the universe was never truly empty. Even before the Big Bang, there would have been quantum fields. Even in the emptiest regions of intergalactic space, there is activity. Even in a perfect vacuum, there is something. The concept of pure nothingness does not exist in our universe. It cannot exist. Physics forbids it. Richard Feynman had a particular gift. He could hold two things in his mind at once: the rigorous mathematics of quantum field theory, and the profound wonder at what that mathematics was revealing. And yet, somehow, we can understand it. But physics cannot tell us why. That question remains open. Perhaps it always will. So where does this leave us? It leaves us with a universe far richer than we imagine. What looks like empty space is actually the foundation of everything. The vacuum is not the absence of reality. It is the ground floor. You are walking around on that ground floor right now. You are breathing it. You are made of it. The fields that fill empty space are the same fields that give rise to your atoms, your thoughts, your experience of being alive. Feynman tried to build physics without fields, and he failed. But in that failure, he discovered something more profound. Fields are not optional. They are not a mathematical trick. They are the deepest description of nature we have found. And the vacuum, that supposedly empty nothing, is absolutely essential. It mediates every force. It enables every interaction. It is the substrate from which all particles emerge, and into which they return. Nothing is doing most of the work. The next time you look at empty space, the gap between your hand and the table, the air in your room, the void between stars, remember what you are actually looking at. You are looking at quantum fields in their ground state. You are looking at zero-point fluctuations. You are looking at one of the most active, dynamic, mysterious things in existence. You are looking at nothing, and nothing is more full than you ever imagined. That is the universe we live in. That is the discovery Feynman made when his theory without fields finally failed. And that is why understanding it changes everything about how we see reality. The theory that almost worked was simple and elegant. But the theory that actually works, quantum field theory, is simple and elegant and true. And truth, as Feynman knew better than anyone, is always more beautiful than our first guesses. Keep looking, keep asking, keep wondering. Because if nothing turns out to be something, imagine what else we have wrong. Imagine what else is waiting to be discovered. The door is open. Walk through, and card channel. Otro, subscribe, Raminda.